So we've got all these different chambers in the heart here. Does anybody want to take a chance at trying to describe the flow of blood through the heart? What happens? You want to do that? You don't want to do that? Okay, so what is this chamber here that's a venous chamber that comes back into this right top side of the heart called?
Right atrium.
The blue thing, the veins.
Pulmonary vein.
Superior vena cava. And you actually have the inferior vena cava, which it doesn't show on here. So the inferior vena cava and the superior vena cava go back to what chamber in the heart? On the right side. Right atrium. Good job. So why is the blood, why do they represent it as being blue, even though it's not really blue? Why? There's no more oxygen. What happened to the oxygen? Where'd it go? Well, it went to the cells, and what did the cells do with the oxygen? They make ATP, they burn sugar. You had an oxidation reaction with sugar, so you could burn it, combustion, right? So we can make ATP, energy. So it comes back into the right atrium, and then where does it go?
Right ventricle.
Right ventricle through this little valve here. And then the right ventricle, it pushes it through pulmonary artery, and it goes to the lungs. And what happens in the lungs? The blood's mostly CO2 now.
Exchange with oxygen.
So it goes from the bronchial tubes to the bronchi to the small tubes to the alveolar sacs. And the alveolar sacs are surrounded by capillaries. So there's capillaries all over the alveolar sacs. The alveolar sacs are only one cell thick. They're like little balloons. They collapse real easy. The pressure has to pop them back open. They're so thin that the alveolar sacs and the capillaries are both only one cell thick. So the CO2, which is low in the lungs right now, the lungs are full of oxygen because you breathe air in, but they're high in the blood. So which way does diffusion work? Does it go from high to low or low to high?
High to low.
High to low. So because the lungs are full of oxygen, all that oxygen is going to go towards low, which is the blood. And all the CO2, which is high in the blood, is going to go towards low in the lungs. So you're going to exchange CO2, you're going to give that to the lungs, and the lungs are going to give oxygen to the blood. Okay, that happens up in the lungs. And then where does it go after that? After you get rid of the CO2 and you gain the oxygen, then where does the blood go? From the lungs. What's the next chamber it goes to? The left atrium. And the left atrium pumps it through the left. And then the left ventricle pumps it through a big, strong valve. What's that valve called?
Aortic valve.
It's a heart valve. It's called the mitral valve. It's the most important valve in the body, in the heart, because if it leaks, it really affects cardiac output. Mine leaks 20%. That's why I'm not supposed to play sports. So I really listen to those doctors, right? I never played any sports. I ran a 430 mile with a bad heart valve. So anyway, so the heart contracts, the left ventricle contracts, and then where does it send the blood after that? To the rest of the body. And what's the big, there's one in the bottom coming out, doesn't show it here? There's one coming out here, and one going out here. What's the one going up called? Ascending aorta and descending aorta. Sumet, all these every part that I'm talking about is going to be on the next test, and this whole flow that we're reviewing is going to be on the next test. That's going to be like one of the biggest test questions, or at least tests. You have to go through the heart and all the different things. And I made my own study guide. I guess I'll show you some pictures from that too. We're going to go over the PowerPoint in just a second. Yes, this one.
Deoxygenated blood goes to the left atrium.
Okay, so the blood comes back from the superior and the inferior vena cava. And it doesn't have oxygen, it's full of CO2, the oxygenated blood. And it goes into the the right atrium. The right atrium fills up the right ventricle. And the right ventricle pumps it up through the pulmonary artery to the lungs. When it goes to the lungs, what happens? You got oxygenated, you got deoxygenated blood, now it goes to the lungs. What happens in the lungs? Oxygen binds to the red blood cells, and it does that. It goes from the capillary into the alveolar sac. It comes from the alveolar sac and goes into the capillary. I said that backwards, I'm sorry. And then the oxygen binds to the iron part of the hemoglobin molecule. Okay? So basically the blood becomes oxygenated. Then the CO2 goes into the lung so you can exhale. So there's an exchange of gases there. We get rid of CO2 and we take in oxygen. Yes? Yeah, the alveolar sacs, the alveolar air sacs, they're like little mini balloons. All your lungs have those. If you smoke a lot for a lot of years, you'll pop all those alveolar sacs, and you can't exchange the CO2 and the oxygen, and you're in big trouble because you build up too high concentrations of CO2 in your body, which makes you really acidic, and you can't get oxygen for doing cellular respiration, so you can't make energy. So those are really important. The capillaries. So the oxygen's in the alveolar sacs, and it goes into the capillaries, because the capillaries surround the alveolar sacs. Every alveolar sac is surrounded by capillaries, and they're only one cell thick. So it's really easy for the air, the gases, to diffuse. The CO2 diffuses into the alveolar sac, and the alveolar sac, where the concentration of oxygen is high, it diffuses into the low concentration into the red blood cell, into the capillary. So it always goes from high to low, simple diffusion. But they have to be in close proximity, and they have to have just one layer of cell so that they can exchange the oxygen and CO2. That's why the alveolar sacs are so important. They have to have this high surface area, they're very thin for the diffusion to work. But that's why they're what are destroyed the most when you smoke cigarettes, because they're so thin and delicate little balloons. Okay? So then once the lung exchanges the gases, it pumps it into the left atrium, the left ventricle. Then the left ventricle goes, that's systole, that's the biggest, largest sound of blood up, and then it goes throughout the rest of the body. Okay? So Allison, I just covered a whole bunch of stuff about the heart. What did you get from that, or what are you not sure about on the heart? The diffusion part, okay, that happens at the alveolar sac, the little balloons, and they're surrounded by capillaries. The capillaries are only one cell thick, the alveolar sac is only one cell thick. So when you breathe in air, you fill the lungs with oxygen, right? So there's high concentration now in the alveolar sacs. Now the blood that's going up, that's getting pumped from the right ventricle up to the lungs, has a high concentration of CO2 and low oxygen. So it's got low oxygen, the alveolar sacs have high, so it's going to go from the alveolar sacs, diffuse to where it's low, into the capillaries. Now the capillaries have high CO2, and it's low in the lungs, so the CO2 is going to go from high to low into the alveolar sacs from the red blood cells. It's high concentration in the alveolar sacs because you just breathe in. Okay? Go to low into the blood where the oxygen is low. Now the blood has high CO2 and the alveolar sacs are low CO2, so it's going to go that way. So we're going to exchange, we're going to get rid of the CO2 and take in oxygen to the capillaries. This, they go back into the heart, into the left atrium, which pumps up the left ventricle, and the left ventricle perfuses the whole body with fresh oxygenated blood. So now each red blood cell has a heme group on it, made of iron, and each one can hold like 200 oxygen molecules, or can hold 200 CO2 molecules. I'm not 200, I said that wrong. Millions, like 2 to 3 million oxygen molecules, or a million CO2 molecules. Okay? So that's how it works. That's the whole part. Okay? So let's look at a quick video on smoking. And
we can take in oxygen and then get rid of carbon dioxide. And right here in Montana at around 5,000 feet, that's no big deal. But if I were to climb Mount Everest, the higher I go, the less oxygen there's going to be. And that's a real limit to our ability to climb very high. And so it wasn't until take in oxygen and then get rid of carbon dioxide. And right here in Montana at around 5,000 feet, that's no big deal. But if I were to climb Mount Everest, the higher I go, the less oxygen there's going to be. And that's a real limit to our ability to climb very high. So it wasn't until 1953 that Sir Edmund Hillary and Tenzing Norgay finally climbed Mount Everest for the first time. You can see Tenzing Norgay right up on top, the first photo ever taken from the top of Mount Everest. It wasn't until 1953, but if you can't see on his back, there's a huge canister that contains oxygen, and that leads into his mouth because they had to take oxygen with them. And so it wasn't until, I think, 1971 that somebody was able to climb all.
why is it not showing the bottoms? Okay, so why did they have to take oxygen up there to climb Mount Everest? Not enough oxygen in the atmosphere at 29,000 feet. And basically, anything above 26,000 feet, you're starting to die. Your lungs are filling up with fluid, there's not enough oxygen, it's a bummer.
And Tenzing Norgay finally climbed Mount Everest for the first time. You can see Tenzing Norgay right up on top, the first photo ever taken from the top of Mount Everest. It wasn't until 1953. But if you can't see on his back, there's a huge canister that contains oxygen, and that leads into his mouth because they had to take oxygen with them. And so it wasn't until, I think, 1971 that somebody was able to climb all the way up Everest without using oxygen. And that they do that by going up to a base camp, move up higher, move down, move higher, move down, move higher, move down. And so their body's starting to accommodate to that change in the elevation. And even that, pretty much dying at the top because of that lack of oxygen. And so basically, animals have figured this out in a number of different ways. If you're a worm, your respiratory surface is actually going to be your skin. You're absorbing oxygen and getting rid of carbon dioxide through your skin. So their skin has to be moist. And they have to have a large surface area. If you're an insect, you use things called spiracles. So basically, there are holes on the side of an insect. They go to tubes, they go to more tubes, and more tubes, and more tubes, and more tubes. And an insect actually has tubes that almost go all the way down to the level of cells. And so you have to have a huge surface area is one thing you need, and then it has to be moist is another thing. And so the two big things I want to talk about are gills. So gills is a way that fish have solved this problem. And then lungs, and that's the way that we've solved it. And so what's the difference between fish and us? Well, fish live in an area that's really, really moist, so they don't have to worry about that. And so their gills just sit right out in the water. But they also live in an area where there's not much oxygen at all. And so they have to have a very efficient way of exchanging oxygen. Us, well, we have to fold our lungs inside our bodies so we can keep them moist. But there's so much oxygen in the air relative to the amount that's in the water that we don't have to be as efficient. So how efficient do the gills actually have to be in fish? They can reclaim something like 80% of the oxygen that's in the water. So they're really, really efficient. We're not even close to that. And the way they do that is they use something called countercurrent gas exchange. And so basically, as the blood flows through the gills, the blood is going to flow like this. So all the blood is going to flow in this direction, and then it's going to flow out the other direction. So in the gills, it's going in that direction, and it comes out in the other direction. But the water is going to flow in this direction. And so what you have is the blood flowing in this direction, and then you have the water flowing counter to that. And so as they go like that, it pulls water in over their gills, but the blood is moving in opposition to that. Engineers use countercurrent exchange quite a bit, but basically what is it doing? Well, if you think about this is going to be the dirtiest of blood down here, and then it's going to get cleaner and cleaner. In other words, it's going to get more and more oxygen. But what what it's doing is, as it gets more and more oxygen, it's meeting water that's more and more fresh. In other words, it has more of the oxygen present. And so by putting blood in the opposite direction, it's really efficient at getting that oxygen outside water. Now, us, we don't have that problem. We do have a problem with moisture, and so we actually have to fold our gills inside our body. They're not gills, but we fold our lungs inside our body. And so we have a trachea that leads down into bronchus and then bronchioles all the way down into the alveoli. One thing that's important, though, is that it goes in, and then that's it. In other words, it's one-way flow. When we breathe in, it goes in, and then that's the end of it. And so if you take things in, like if you smoke, all the material that comes in is going to go into your lung.
So when you breathe in smoke, cigarette smoke, or pot smoke, or diesel fumes from here being in Yangon, there's all these cars are diesel. It just goes in, it doesn't go back out. Fortunately, you have these little things here that look like air. These are cilia, and they line all the bronchial tubes, and they help to kind of like sweep all that dirt and trash and debris out. But when you smoke for a few years in a row, you actually kill the cilia, so they can't sweep and clean the lungs. So then the stuff just stays in there. I was watching an experiment this morning that they did. They took a pig, these two pigs, and made one pig smoke. One pig's not smoke. And they forced smoke into these pigs. And even just like smoking 60 cigarettes, one pig's lungs were still pink and perfect. One that didn't smoke, the one that smoked 60 cigarettes worth, the lungs were totally black. And the breakage and trachea tube for just 60 cigarettes. And most people will smoke 60 cigarettes a day. People that get really addicted to nicotine. You know, so that's what happens. So that's why it's bad.
And then there's no out. And so if you breathe a lot of coal dust, it's going to go in, and then it gets stuck in there. Or asbestos goes in and gets stuck. And so the lining of the trachea, the lining of our respiratory system has these cilia on it. And so basically what happens is those little hairs are going to move material out of your body so you can cough it up and eventually swallow it. Another cool thing about this is that it really looks, let's even go to this level, it almost looks like a tree upside down. And so basically what's happening is that we are increasing the surface area by having the trachea go to the bronchus and then the bronchioles, and then they just keep branching and branching and branching. Again, why are they doing that? They're doing that to increase the surface area.
And what are they in? What's the surface area increases the most at the very end? What's it called? The little balloons. Alveolar sacs, alveoli, or alveolus. So those are the things that pop if you smoke cigarettes 30, 40 years, and you get a disease called emphysema. Like I said, my friend Larry, we used to surf at his place down in Mexico. We used to go down there and fix things for him. So he let us stay there for free. And I held his hand and watched him die in front of me. Even though he was on pure oxygen, he wasn't getting enough oxygen in the brain, and his brain stopped, and his heart stopped. Even though he was breathing pure oxygen, because he smoked like something like 45 years, maybe 50 years, and he just those alveolar sacs were all popped, so he couldn't exchange the CO2 and the O2, and he suffocated while he was.
Okay, so let's get to the level of that oxygen exchange. So how do we get oxygen in? Well, basically, if you were to look here in the capillaries, let's imagine this out here is the space in the alveoli. So now we have air coming in, so we have air out here. Basically what's going to happen is these red blood cells, as they move through the capillaries, that oxygen that's inside the alveoli is going to move in. And so these red blood cells are almost in direct contact with the capillaries. Now where's the oxygen going to be stored? We have a chemical called hemoglobin. Hemoglobin is a protein, and that's stock full inside of all of our red blood cells. That's why it's red. So
These are the alveolar sacs, and these are surrounded by capillaries. And it's this close. The red blood cells, they have to stack up and line up to fit through the capillaries because they're so small that only one red blood cell can fit through at a time. And this is the alveolar sac here. So it's so thin that oxygen can diffuse out of the lung and bind to the hemoglobin on the red blood cell. And then all the CO2 on the red blood cell can go out back into the lung of the alveoli. So it's actually like this. And there's going to be a whole bunch of test questions on this. I know Mr. Rick really loves this part of it. And there's a video on just capillaries I was going to show you today. I don't think I'll have time to show you today. So this little part that he's talking about right now is the bottom line of that whole capillary video. I will show it to you. I meant to show it next class. But anyways, that's what's happening there. That's important to understand the gas exchange. And because that's why these are so fragile. That's why they're damaged by smoking cigarettes or marijuana or pot. They're damaged by it because they're only one layer thick. They're very delicate.
Basically, inside the hemoglobin, we have these iron molecules. One there, one there, one there, one there. And that iron is going to bond to the oxygen that's found inside the air. And so, why is it red? It's because it literally is rusting. The oxygen is attaching to the iron.
So isn't that bummer? We have to breathe every day, all day long, to burn sugar, to keep our brain alive and our heart alive. But by doing that, we're oxygenating ourselves and we're creating like rust in our body. We're wearing ourselves out from the inside out, unfortunately. That's why it's really, really important to eat a lot of vegetables and fruit every day because they're very high in nutrients called antioxidants. Antioxidants actually help slow down the aging process that we have from burning sugar. We burn sugar in the Krebs cycle and the mitochondria and the electron transfer chain. We release a lot of dangerous chemicals called oxidants. Okay? And but we have to do that to keep ourselves alive. So that's why it's important to eat lots of vegetables and fruits because they have antioxidants in them. You'll know that it does because they're always like, it's something that can stain you. Like you eat a pomegranate, if you get it on your shirt, it's going to stain it. If it's a bright color like purple or dark orange or something like that, it's full of antioxidants. If you look at like pumpkin, pumpkin's orange, right? You know it's healthy for you because it's got bright color. Like pomegranate juice, grape juice, if you spill it on yourself, blueberries, if you get them on yourself, it's going to stain it. But that means they're high in antioxidants. A sea berry, which you guys don't have, it's from Brazil, it's more popular in California. ACHCI berry, a sea berry or something like that. It's a purple berry, and it's really high in antioxidants. So it's good to eat lots of fruit and vegetables every day so you don't age as fast.
Giving us that red color. And so that's where the oxygen is going to bind. It's going to bind to that heme group or the iron inside the hemoglobin. What about the carbon dioxide? Well, the carbon dioxide is not really contained within the red blood cell itself. Basically what it's doing is it's being converted to bicarbonate. So we're converting that carbon dioxide with water to this bicarbonate. And a lot of that bicarbonate will actually be right here inside the plasma of the blood.
So did you catch that? Uri, did you hear what they said? They said the CO2 is not only carried on the red blood cell, it's actually in solution in the plasma as bicarbonate. So because it's in the solution, though, it can diffuse in the solution through the one layer to get into the alveolus so we can exchange it. Okay? So it gets converted back from bicarbonate into CO2 in the lung. Okay? So that's an important thing to understand.
Some of it will be in the blood cell, but most of it's in the plasma. When we get here to the alveoli, we've got enzymes that control all of this, and that's going to release as carbon dioxide. So carbon dioxide goes back into the alveoli, and we breathe that out. We take in.
And I'm not going to make you learn all those enzymes that convert it from bicarbonate back to CO2. Don't worry about that. You don't have to learn that. You just have to know that you have to exchange CO2 and oxygen. And the CO2, some of it's not stuck on the red blood cell, but most of it's actually in solution in the plasma. Okay? But you don't have to learn any of the chemicals or the enzymes that convert bicarbonate back to CO2 gas to go back and forth.
And over and over and over again. And so that's a respiratory system. It doesn't work.
Come on up. No, Terry, come on up. Okay, so today the students are helping me teach the class again. We're doing expert, and we're working on a really difficult concept today. It's how a muscle contracts. There's lots of steps and chemicals involved. And Theory's going to come up and help me do it. Come on, Theory, you can do it. I will help you. I promise. Come on up. Come on up. Okay. Gentlemen, will you please pay attention? So Theory, we're going to talk about how a muscle contracts today, right? So what is, Petrus, shh, be quiet. What is this thing here called?
Axon, and this is like the synaptic cleft.
Synaptic cleft.
And this is the cell body.
And this is
This
another.
is another axon. These are sarcomeres.
Those are called sarcomeres. So what is a sarcomere? What does it represent?
It's like it's a like site where the myosin binds to the axon.
Yeah, and so that's what makes it a muscle, the working part of a muscle fiber, right?
It's a contraction. It makes the muscle contract.
Okay, good. So how do we get signals down the axon? Where does this start? Where does it start?
Start with the brain, and it goes down the spinal cord, and then it comes out of the neck. Like
If it's going to the arms,
it's going to the arms.
it comes out the. What do we call these neck nerves in here called?
The neck nerves.
Those are called cervical nerve roots. They come out of the neck area, the cervical spine, and there's the brachial plexus that controls everything in the arms, right, and the shoulders.
Yeah.
So you have a signal coming down here.
And they have
So-
to cross the synaptic.
So how does it get across the synaptic cleft? What chemicals are involved in that?
Chemicals.
There's three chemicals. Well, you need acetylcholine, but what has to happen for the acetylcholine to cross? What's the first thing that the nerve signal releases?
They release calcium.
Calcium.
Calcium and like sodium.
Well, calcium.
Right.
Okay, that's okay.
Calcium.
You releases calcium,
Yeah.
and the calcium causes the vesicles to release a neurotransmitter. What's that neurotransmitter called?
Neurotransmitter. Wait, I know that. The neurotransmitter.
You already said it.
Acetylcholine.
Acetylcholine. And then that changes on the other side. It changes the permeability of an ion. It's in salts. What's that ion called?
The iron is like
Sodium.
Yeah.
Okay?
It makes it permeable.
Yeah, and it makes it more permeable. So that propagates the nerve message. And then the same thing happens down here. There's another, I didn't draw it because I drew it real quick just now.
There's another axon, so
Okay. So when it releases sodium, which makes the vesicles release ACH across the synaptic cleft, and then that creates the increase in permeability. I mean, it releases calcium and sodium. So then what happens at the sarcomere? Let's draw another picture up here real quick.
The
Okay.
sarcomere, there's an axon, and then it wants to bite.
This is the Z line.
The myosin wants to bite to the axon, but there's like this H zone,
I didn't draw it pretty good.
and then like they close the H zone.
Okay. That's the H, so I draw it bad. Okay. So I'm going to try to draw some things here.
Oh yeah. The upper one is the axon, right?
This is
The upper one is the axon.
This is the myosin,
The lower one is the myosin.
and this is the actin.
Yeah. The actin.
Yeah, good.
Actin.
So what happens? How does the myosin? Actually, I drew it wrong. The fingers would actually point this way. Sorry.
They have like fingers, and then they bind like this, and then they close the H zone.
So the fingers bind, pull, release. Bind, pull, release.
They bind, pull, release. Wait, they bind.
Frederick, I know you're helping Petrus out, but don't do it right now. Be quiet. We're recording, okay?
They bind, pull, and release. So
And then what happens to it? Can you show me with your fingers?
It's like the H zone closes.
The actin,
The H zone closes because the actin binds to the myosin.
the myosin binds to the actin, and it slides the actin along
Yeah,
and closes the muscle. And what does the muscle do when that happens?
it contracts.
It contracts or shortens.
What about a triple myosin?
Well, yeah, I don't know if I'm going to put that in test because it's complicated. You have to have the
Calcium to like
block the tryptomyosin so it'll
the myosin to reach the
to attach to it. Yeah.
Yeah. So in here, like where would the tryptomyosin?
It's I have to draw another drawing to do that. But the tryptomyosin blocks the blocks it from the myosin from attaching. So you have to release that first. Okay? But you did a great job. Thank you. Good job, Terry. She was the only one brave enough in the class to come up here and do this. Okay? So I'm going to have Daniel talk about a concept about Daniela talk about oxygen debt. So what happens with oxygen debt? Why, like if I was going to run around a track and try to run a mile, why do I start to run slower towards the end? What happens?
You get tired, and like to make ATP, you need oxygen, so it will go through like glycolysis, the Krebs cycle, the electron transport chain. But when your body starts to lose oxygen, you can't do the Krebs cycle and electron transport chain. So after glycolysis, you get 2 net ATP and pyruvic acid, and those go to the fermentation. Then the lactic acid goes to your muscles, and it'll like contract and like ache.
Okay, so what if I had plenty of oxygen and I wasn't oxygen? Normally, what would the body do with the pyruvic acid after glycolysis? Normally, if I had plenty of oxygen in and I did glycolysis, what would the body normally do with the pyruvic acid? Where would it go next? You're going to take it into the mitochondria, and you're actually going to convert it into NADs and fats. Remember? And what's that step called? The Krebs cycle. But you can't do the Krebs cycle. You can't convert pyruvic acid into the NADH plus and FADH plus. And because of that, you can't do all the 40 steps of the Krebs cycle. So then you can't get to the electron transfer chain and make electrons, right? Okay, good job. Excellent. Okay, Freddie, stand up. Come over to the skeleton. Okay. Explain all the bones in the skeleton for us.
We start with the cranium, the maxilla, the mandible.
Go slow and speak clearly and loudly, please. This is the mandible.
The mandible.
This is the cranium. What's this thing here called?
The cervical vertebrae.
Cervical spine. How many cervical vertebrae are there?
I think in the first, in the neck, 7.
7. How many vertebrae are in the mid-back?
12.
And what are those called? Starts with the T. The thoracic. How many are in the low back here? This here.
8.
No, there's 5 lumbar vertebrae. 5 lumbar vertebrae. Good. That's more than we asked them to learn. So what's this bone here called?
The scapula.
Scapula. And you have all the muscles in the back attached to this, and the shoulder muscles and the bicep attaches to this. What's this one called? Here.
The clavicle.
Cool. Cool. And what's this one here called?
The humerus.
Humerus. It's a funny bone, huh? So where's the bicep go?
The bicep goes here. No, the bicep goes here.
Okay, so where would the origin of the bicep come from?
From here.
It would come from actually the coracoid process of the scapula and the arm. So it would be up here in this. Is this proximal or distal? Or distal? Is this closer to the meridian line, or is this closer out here?
This is closer.
So the origin is proximal. The insertion down here on the elbow is distal. So if you shorten that muscle, what's it going to do to the arm?
Extend
It's going to bend it.
Bend it.
It's going to flex it.
Flex it, and then you can.
So what's the big muscle that's back in the back of the arm called?
Tricep.
It's got 3 heads. And what's that going to do to the elbow?
It's gonna release it.
Extend it. It's going to cause extension.
This is gonna pull, and then this is gonna bend.
Yeah, this is going to flex it. Flex it is shortening a joint. Extension is making a joint go longer. Flexion, extension. Okay, good. What do we call all the bones in the wrist?
The carpal.
Carpals. How about in the hand here, like the fist part?
Metacarpals.
Metacarpals. How about these?
The phalanges.
Phalanges. Okay, so what do we call this big bone here?
The pelvis.
The hip bones.
The pelvis.
Pelvis. What about the big triangle-shaped bone in the back? Come back, point at this one.
It's not the S, I forgot.
Sacrum.
Sacrum.
And what's the tip of it called? Coccyx. Okay, what's this biggest bone in the body called?
Femur.
The femur is the thigh bone. Yeah, the hip flexors come from the spine, and they come down here and hook on this bump here. That's called the lesser trochanter. All the butt muscles, the gluteal muscles, attach to the greater trochanter. So these bumps on the bone are for muscle attachment. They're called prominences, okay? This is called a trochanter, okay? So what's this little bone at the knee called?
The patellar.
Does anybody know what the patella is for? Why do we have a sesamoid bone at the knee there?
To attach.
Well, it's actually to protect the knee so all the quadricep muscles don't rub across this joint here, because it could rub here. And this makes it slide, so the tendon, which attaches down on the tibia here, the tibial tuberosity tendon doesn't get frayed. So sesamoid bone gives mechanical advantage and leverage and protects the tendon from getting roughened up. That's what, in my toe, my big toe, I have 4 sesamoid bones in my big toe. I know because I've broken it 3 times in martial arts. So it's kind of unusual. Usually they only have 1 sesamoid in your big toe. I have 4. I don't know why. So what's this big bone here in the shin called, the weight-bearing one?
Tibia.
Tibia.
The fibula.
Fibula. So what are these bones in the foot called?
Tarsals and metatarsals.
Tarsals and metatarsals.
Phalanges.
Phalanges. Okay.
I think you both have that.
Oh, we forgot these. What are these here called?
The radius and the ulna. The radius goes to the thumb,
Mm-hmm.
and then the ulna goes the other way.
Yeah, I think that one of these models, they put it together. It's on the wrong side. They put it together wrong. Awesome job, dude. Does anybody know the muscles? Does anybody know the muscles yet for the test? Nobody knows the muscles very good? Roland? Nobody wants to do the muscles? Okay. I'll work through the muscles. We'll do the muscles. Okay, so I'm going to do the muscles. Okay, you guys probably know them anyways, but we'll do them anyways. So, I don't think we made you guys learn the muscles in the face, right? For the test. Masseter, we won't get into it because it's probably too much. What is this big muscle in the arm called, guys? Bicep. Bicep?